Alright, in this video we are looking at the properties of definite integrals. Now the definition of the definite integral of f on the interval from a to b specifies that a be less than b. Okay? However, it is convenient to extend the definition to cover cases in which either a equals b or maybe a is even greater than b. Now, geometrically, the next two definitions seem reasonable. So, for instance, it makes sense to define the area of a region of zero width and finite height to be zero. Okay, so think about this. That first one says that if f is defined, as long as f is defined at x equals a, then the integral from a to a equals 0. So we're talking about from a to a. So we have no width, so our base is equal to 0, but our height can be whatever. But it doesn't matter because 0 times anything is 0. So if delta x equals 0, then you get a big goose egg. Okay? Now the other one would be that if f is integrable on a to b, then if we switch the limits of integration, all it does is change the sign of our area, because basically we're just going backwards. Okay? So let's look at a couple of examples of this. Say we want to evaluate this definite integral, the integral of sine from pi to pi. Right away, if a and b are equal, we know that our integral is 0. What about x plus 2 from 3 to 0? Well, we know from a previous example that the integral from 0 to 3 of x plus 2 dx is equal to 21 over 2. Therefore, if we switch the limits of integration from 3 to 0, x plus 2 dx would be negative 21 halves. Okay? Now, in this figure, the large region can be divided at x equals c into two subregions whose intersection is basically a line segment. Now, because the line segment itself has no area, it follows that this area plus this area equals the total area. Right? So basically, I'm saying I can split up one interval, or one integral, into two separate integrals. So instead of going from a to b, I go from a to c, then from c to b. But notice, as long as these connect, then I can just do these. Okay? So, let's use the additive interval property to show what the integral of absolute value of x from 1 to negative 1 is. Or from negative 1 to 1, sorry. So, let's think about this graph. This graph, negative 1, 1, looks like this. Right? Now, what if because here, this is the graph of f of x equals negative x, whereas this is f of x equals x. So I can break this up into two separate, from negative 1 to 0, of negative x, plus from 0 to 1 of just x. Don't forget our dx's, right? So, this is just a triangle. It has 1, 1. So I know that the area of this is 1/2, 1 times 1, plus the area of this one, that's also 1, that's also 1, 1/2, 1 times 1. So I get 1/2 plus 1/2, which equals 1. Now, theorem 4.7 is a couple of properties that we use, and they're very similar to properties that we've used all along. If you've got a k, you can bring it out front. If you're taking the integral of sum or difference, it's just the sum or difference of the individual integrals. Okay? Notice that this can also be extended to cover any finite number of functions. If I'm adding 20, it doesn't matter. I can separate it into 20 separate integrals. All right, so let's evaluate the integral of negative x squared plus 4x minus 3 from 1 to 3 given that we know these specific values. Okay? So we know we can split this up. We could say that we go from 1 to 3 of negative x squared plus from 1 to 3 of 4x minus from 1 to 3 of 3, making sure we have our dx's on every one of them, okay? Now, we know that we can pull that minus sign out front, so we get the integral from 1 to 3 of x squared dx. Here we can pull the 4 out from 1 to 3 of x dx, minus, here we can pull the 3 out from 1 to 3 of just dx. So, if x squared, the integral from 1 to 3 of x squared is 26 thirds, this is negative 26 thirds, plus 4 times the integral of x is 4, minus 3 times the integral of dx, which is 2. So we get negative 26 thirds plus 16 minus 6. We get our calculator out. We get negative 26 thirds plus 16 minus 6 equals 4 thirds. Okay, if f and g are continuous on a closed interval from a to b, and f is always less than g but is always positive, okay? So notice f is always positive, it's always non-negative, not always positive, but always non-negative, and it's always less than g. As long as a is less than b in this interval, then the following properties are true. First, the area of the region bounded by f and the x-axis has to be non-negative. There has to be some area in here, right? Second, the area must be less than or equal to the area of the region bounded by g. So g will have a bigger area than f will, as long as g is always bigger than f. This just kind of logically makes sense. These two properties can be generalized here. So, theorem 4.a is called the preservation of inequality. So if f is integrable and non-negative on a to b, then it has to be non-negative. Okay, the area has to be non-negative. The definite integral has to be non-negative. Now, if f and g are both integrable on the closed interval and f is always less than g, then that tells us that the integral of f has to be less than the integral of g, as long as we define them both over the same interval from a to b. So if you have any questions about this, make sure you shoot me a reminder or ask questions in class.